Cosmology is the study of the nature of the universe itself, arguably the most fundamental question astronomy can probe. How big is the universe? How did it begin? What is the universe at all? It's a field that can humble the most narcissistic of kings, one that inspires personal transformations from nihilism to humanism, and one that in recent years has been claimed to be facing a crisis so severe it threatens to undermine our very physical models of the cosmos. I am, of course, speaking of the Hubble Tension, the so-called crisis in cosmology. Like any active area of research, this is one where the needle is rapidly moving as new analyses and data are pouring in on an almost daily basis. Yet despite all that, we do have enough information in hand now to say that something appears to be very wrong. So today, let's break down what is this crisis and what might it really mean. No sensationalism, just the facts. The story really begins in the late 1920s when observations of distant galaxies revealed that the further away a galaxy is, the faster it appears to be moving away from us. Both Edwin Hubble and Georges Lemaitre independently realized that the universe must be expanding in order to explain this. Like stretching a piece of rubber with marked points, every point thinks that every other point is moving away from it during the expansion, and indeed the points furthest away seem to move faster. In the early 20th century, the rate of expansion was difficult to reliably infer, but over the years, astronomers have improved their ability to measure this expansion rate, which has become known as the Hubble constant. The Hubble tension refers to a disagreement about this value. In particular, this number has been measured with two independent methods, which seem to give answers which are sufficiently different that they are difficult to reconcile. Either one of these methods is wrong, or there was something wrong with our understanding of the cosmos itself. The first way we can measure the Hubble constant is from the cosmic microwave background, or CMB for short. This is the earliest light we can detect in the universe, emitted at a time when the cosmos was less than 400,000 years old, so that's 13.8 billion years ago. At first glance, the CMB appears remarkably uniform, with the universe appearing to have an average temperature of about 3 Kelvin in all directions. But subtracting off that average, the patterns and inhomogeneities that are revealed encode information about the shape, composition, and structure of the universe. Remarkably, just about everything within the CMB can be described by a physical model using just 6 free parameters, describing the mixture of matter, and dark energy, as well as the shape of the universe and its expansion rate. The agreement of this model to the data is frankly remarkable, with the recent Planck mission revealing almost perfect agreement to the model across the board. By running this cosmological model forward in time, one can predict what the current rate of expansion should be. Over time, we've got better at making that measurement, with early results from the WMAP satellite giving a result of about 72 plus or minus 5, but now more precisely pinned down to 67.4 plus or minus 0.5 using the Planck mission. I'll ignore the units here because it's really not that important for the current discussion and largely just distracts from the main points. The real thing to take away here is that all of these measures are within error of each other and look consistent with just improving our precision over time. So if this cosmological model is correct, which remember it does a remarkably good job of explaining the CMB data, then we really should expect that the modern universe around us is expanding at its predicted rate. But of course, we don't just want to trust the math. Astronomers actually want to double check that number. So we've been going out, taking the local universe around us and measuring its expansion rate to make sure that everything agrees. These methods largely build upon what Edwin Hubble was doing almost a century ago, measuring the distances and velocities of distant objects and putting them on a graph to get the expansion rate. The devil is in the details though, for measuring the distance to objects is particularly nuanced and challenging when dealing with objects that are millions of light years away. If I want to measure the distance to a nearby object, the way our brains do it is with parallax. Hold your finger out at arm's length in front of some distant background, like say a city skyline, and if you close one eye and then the other, your finger will seem to move from side to side relative to that background. That's because your eyes are in physically different locations, and so the angle subtended from each eye to your finger is different. The closer your finger is held to your eyes, the bigger the shift. However, as we move our finger away, the shift becomes less. So in this way, the parallax shift gives us the distance to an object, and we do the same thing in astronomy, except the spacing between our eyes is replaced with the orbit of the Earth from summer to winter. The Earth physically shifts by 300 million kilometers over 6 months. The Gaia spacecraft is a master of measuring parallax, and it has now done so for millions of stars. But the further away an object is, the smaller its parallax will be, eventually becoming so small that we can't detect it even with Gaia. To get around this, astronomers need a new distance measure, a distance proxy, and so that's where a special type of star enters the story, one called a Cepheid variable. All we really need to know is that Cepheids are massive stars that regularly pulse, causing their brightness to periodically increase and decrease. These are very bright objects detectable from across intergalactic space, and it was Henrietta Leavitt who discovered that their pulsation periods were intimately related to their brightness. Leavitt turned Cepheids into so-called standard candles, which are invaluable to cosmologists. The basic idea is that you first measure the distance to a nearby Cepheid using parallax, which, practically speaking, means it has to be one within the Milky Way in order for that technique to work. Step 2, very simply, you just measure how bright the Cepheid appears here on Earth. Step 3 is that you calculate then how bright the Cepheid must truly be given its distance using the inverse square law. And step 4, you observe its pulsation period. Doing this for all the nearby Cepheids you can find, you can make a graph of the Cepheid luminosity versus pulsation period, giving this tight relationship. That relationship, known as the period luminosity relation, or simply the Leavitt law, is kind of like your decryption key for measuring distances outside the galaxy. Because having calibrated this law, we can now go out beyond the Milky Way, take a Cepheid's pulsation period, and then immediately know what its luminosity must be. Combine that with its apparent brightness, and you can figure out how far away it must be using the inverse square law, so its distance. And that distance is one of the 2 basic quantities we need to know in order to calculate the local expansion rate of the universe. So you can see that this technique is very powerful, but eventually it stops working for galaxies beyond about 100 million light years. After that, the Cepheids are just too faint for us to detect in the first place. Now that might sound like a huge number, but remember the universe is about 90 billion light years across, so we'd really like to go much further. A key thing to keep in mind is that this technique is wholly predicated upon correctly calibrating the Leavitt law within the Milky Way galaxy. In this way, you can think of it as being like the second rung in a ladder, which depends upon that first rung, which remember is correctly calibrating that law. In fact, we could even go to a third rung, which depends upon the second rung, and in this case, that third rung is Type 1a supernovae. Like Cepheids, these are thought to be standard candles, objects with standard luminosities. But, unlike Cepheids, we've never seen one up close and personal to really know what that standard luminosity actually is. Which is probably a good thing, because those events are so violent that a local instantiation would be undesirable to say the least. And so, in the absence of any local examples, we are forced to figure out the luminosities of these Type 1a supernova using the second rung of that distance ladder, so the Cepheids. In some galaxies, we see Type 1a's go off, and in those same galaxies, we also see Cepheids. That means that we can use the Cepheids to measure the distance to that galaxy, which of course means that that must also be the distance to our supernova. And then we can figure out how luminous the supernova was. So Type 1a supernovae are the third rung on the ladder, and they are so bright that we can look far further out into space, out to distances of now up to 1 billion light years away. But like a house of cards, if any of the layers below are wrong, then our calculated distances to the Type 1a supernovae will also be wrong. And that, in turn, means that if we use them to calculate the Hubble constant, that too would be wrong. It's a precarious game. If you want to measure the Hubble constant to a precision of, say, 1%, and that means that you need to calibrate each of those distance ladder rungs to at least 1% precision, or really even better. The chain is only as strong as its weakest link. So, with our intro to the distance ladder complete, what does it actually tell us about the expansion rate of the universe, Hubble's constant? A team led by Nobel laureate Adam Rees, who call themselves SHOES, have been leading an effort to measure the Hubble constant of the local universe. Similar to what we're seeing with the CMB value, the precision has been increasing over time thanks to more precise parallaxes, refined analysis techniques, and more observational data, which, by the way, includes over 1,500 hours of time on the Hubble Space Telescope. As before, the fact that the value gets more precise really isn't surprising, and each improvement agrees with the previous estimate to within error. So far, so good. But the problem is when we put the CMB measurements back on the same plot. We see a growing discrepancy between them. That right there is the Hubble tension, the crisis in cosmology. So something is very weird here. One of these measurements must be wrong. If it is the local universe one, then that implies that our distance ladder is most likely in error. There must be some systematic calibration issue with what we did there. But if it were the CMB one that was wrong, then that would imply that our cosmological model of the universe is itself flawed. That's perhaps the most exciting of these two options, because it would mean that there was new physics beyond the current model. So what could this new physics be? There's been plenty of exciting suggestions, such as a new particle ignored by the existing model, like the sterile neutrino, for example. Another popular idea is that the strength of dark energy is growing over time, which would have some important consequences for the fate of our universe in the distant future. Others have suggested decaying dark matter, or modified theories of gravity, non-zero spatial curvature, or exotic interactions between dark energy and dark matter. In fact, as you can see, there are quite a few options on the table, but before we start ripping up the physics textbooks and getting too excited, there is, of course, a far more mundane possible explanation, and that is that our local measurement is wrong, that perhaps the distance ladder has been miscalibrated. This isn't just idle speculation. There are good reasons to be worried about the validity of the distance ladder. First, although the Leavitt law was indeed initially conceived to be a simple one-to-one relationship between pulsation period and luminosity, we've since discovered that it also subtly depends upon color and metallicity. That's frustrating because there's actually only a few dozen Cepheids in the Milky Way, so it's going to be difficult to precisely measure these new dependencies from such a small sample to begin with, as well as, of course, challenging to measure those same properties for other galaxies down the road. Metallicity is a particularly challenging topic because for Cepheids, you can't even often measure their metallicity directly. Instead, we rely on the surrounding environment's oxygen abundance as a proxy. The dependency of luminosity upon metallicity is characterized by this coefficient in the Leavitt law equation. It's almost like the exchange rate going from dollars to yen. If you want to know the value of your yen, then you of course need to know the exchange rate to make an accurate conversion. The problem is that astronomers don't really agree on this coefficient, as shown by the range of recently published values shown here. And these differences can introduce discrepancies in the Hubble constant at the percent level. Now, there is some hope that JWST will provide a firm answer here thanks to its improved spectroscopic capabilities, but for now, we may have to wait. Another problem is frankly unavoidable. Cepheids are massive stars, which means they are young stars because massive stars simply don't live very long. So, why is this a problem? It's because stars are typically born in dense stellar nurseries that are nestled within their galactic disk. This is the New York City of the galaxy, a busy, bustling, dense, overcrowded region filled with dust and dirt all over the place. That dust, though, is a major problem, for dust blocks out some of the Cepheids' light, And so we have to carefully correct exactly how much light was blocked out. If we assume the wrong amount of dust though, then we'll get the wrong luminosity for our Cepheid and so break our distance ladder. Who would have thought that something as boring as calibration issues and dust could be potentially responsible for a crisis in cosmology? You hoped for a revolution in physics, and instead you got dust. Indeed, this might sound familiar because it's not the first time astrophysicists have experienced that sensation either. Remember Bicep 2 or Boyagin star, dust, and dust. So to some degree, this is an unavoidable problem with Cepheids. So perhaps one solution is just to ditch the Cepheids altogether, to start over, go back to the drawing board of our distance ladder, and get a new first and second rung. But to do that, we would need to replace the Cepheids with something else. We would need a new standard candle. Enter giant stars. Stars, like the Sun, fuse hydrogen into helium in their core, but eventually they'll swell by hundreds of times as they exhaust the supply of hydrogen fuel in their cores and instead start fusing the hydrogen around the shell of the core. This shell burning behavior leads to a rapid ballooning in the size of the star, which in turn causes the luminosity to greatly rise. It's exactly this process that will eventually doom us all here on Earth. Check out our previous video to see how. Eventually, the pressure in the stellar core becomes sufficiently high that the thus far inert helium ash starts to fuse. This is actually good news because the star is now burning fuel in its core once again, albeit helium fuel, and so now the star returns to a more stable state and thus a smaller size. So if you track the luminosity of the star over time, you'd see this gradual growth during the shell burning phase, followed by a reversal once the helium fusion begins. That reversal point, the peak luminosity, is called the tip of the red giant branch, and it's largely independent of the star's metallicity, unlike for Cepheids. In essence, this reversal point is a standard candle. It's a weird one though, because it doesn't really work for any single object, since it's unlikely you'd happen to catch a star at exactly this moment in its life cycle. But if you look at the brightness values of a large number of giants, then you'd see a clear maximum possible value that corresponds to the tip of the red giants, and that peak is our standard candle. This method is in many ways cleaner than that of the Cepheids, since unlike the leave-it law, there's hardly any dependency on metallicity here, which remember is very difficult to measure at cosmic distances. Yet more, another major advantage here is that these stars are by definition old stars. For example, it would take a star like the Sun about 10 billion years to get to this point in total when counting from its birth. Because of their advanced years, they have long since left their stellar nurseries and have meandered in and around their galaxy many times over. In fact, a large number of them no longer even reside within their galactic disks, but instead have migrated out to what we call the galactic halo, kind of like the quiet backcountry of the galaxy where the spacing between stars is far greater. This is incredibly useful because out here there's hardly anything to get in the way of our observations. There's no dust, there's no contaminating stars. If observing extragalactic Cepheids is like trying to do astronomy in New York City, swamped by the haze and city lights, observing extragalactic giant stars is like being out in the Atacama Desert. Clear, inky black skies peppered with crisp oases of light. Famed astronomer Wendy Friedman has been advancing this method for years, which is not surprising given that it was she who first used the Hubble Space Telescope to measure the Hubble constant 2 decades ago using Cepheids. Suffice to say, Friedman has been thinking about this problem very deeply for as long as anyone. So her team recently used this completely independent standard candle method, the giant stars, as a way of recalibrating the entire distance ladder in an effort to finally resolve the Hubble tension. On the one hand, we have the 67.4 plus or minus 0.5 value derived from the CMB using Planck, and on the other hand, we have the supernova plus Cepheid-based measurement coming in at 73.0 plus or minus 1.0 coming from Shoes. So the real question is, where does this new independent measurement land? Does this third method reveal who's right and who's wrong? Here's their answer, right in the middle of the two. 69.8 plus or minus 1.7. Remarkably, it's actually consistent with both. Whilst the CMB and the Cepheid measurements are 5 error bars apart, or 5 sigma, the tip of the red giant branch method is effectively okay with both of them. It's 1.3 sigma away from the CMB method, which is completely fine, and 2.9 sigma away from the Cepheid measurement. That's a little high, but we could perhaps just explain that by adding in a little bit more systematic error into the Cepheid measurements. In our upcoming Cool Worlds podcast show, which you can look out for in the new year, I asked Wendy what her reaction was when she saw that her measurement landed right in the middle. And I guess we were hoping that your number would land on one side or the other, and we'd be like, okay, so now we know where the problem is. When you realized your answer was right in the middle, were you frustrated by that? How did you feel?
Well, the immediate reaction was sort of like shock. Really? Did it really land in the middle? It was sort of odd, and we didn't attach this absolute 0 point until the end, so we didn't know where this was going to land until we were ready to apply it, and that was it. It was like one morning, here's the answer, and it was slightly a shock.
An interesting way of thinking about the Hubble crisis is to imagine an alternate reality where we invented and deployed the tip of the red giant branch method before the Cepheid method ever came along. So in this alternate reality, we'd have 2 measurements for the Hubble constant, one from the CMB and one from the local universe, and both of them would seem to be in almost perfect agreement with one another. There would be no tension, and instead we'd just be celebrating the remarkable fact that these 2 radically different methods gave remarkable agreement about the expansion rate of the universe. So if then Cepheids came along later, we would likely just dismiss it as a troubled method, especially given the fact that they are usually embedded within bustling galactic disks. So does this mean that there's no crisis in cosmology then? Well, before we totally give up on that idea, I think we still want to improve our precisions just a little bit more. On the horizon, there are 2 big data releases from the Gaia spacecraft that promise to improve our parallaxes even further, and thus will let us go back and recalibrate that distance ladder just a little bit better. Yet more, JWST is already observing nearby galaxies in an effort to measure their distances using both the Cepheid technique and with giant stars, as well as other methods too, to hopefully finally figure out whether they agree with each other or not. So rather than jumping the gun too much, let's just see what Friedman's team find from that sample. A crisis in cosmology makes for a great headline, so much so that it's proliferated across many science news outlets over the last couple of years. It's probably why you clicked this video. And indeed, this video would surely get a lot more views if I told you that physics is broken, or that the Big Bang model is wrong, or some other extreme conclusion, or showed you thumbnails of JWST randomly firing death rays out of it or something. Yes, that really exists. But the truth is often more nuanced, complicated, and often less exciting than that tagline betrays. After all, the answer here may simply be dust. But a headline like dust may be a source of systematic error in Cepheid distance measurements just isn't as catchy as a crisis in cosmology. I can't give you the answers that you might want to hear. That's not how science works. To quote Feynman, nature is there and she's going to come out the way she is. Our predispositions don't count. All I can ever promise you on this channel is a sober analysis, but looking ahead, there will be answers here. From Gaia, from JWST, we will resolve the Hubble tension. So until then, stay thoughtful and stay curious. Thank you so much for watching, everybody. I hope you enjoyed this video. If you did, be sure to like, share, subscribe. It really does make a difference. And if you really want to help us out, then you can become a donor to my research team, the Cool Worlds Lab, right here at Columbia University. I want to give a moment just to give a special thank you to all of our donors over the last year in 2022. And here's looking forward to an even more spectacular 2023.